watching this, we have survived.
The movie The Martian has inspired my four friends, Abby, Anna, Rose, Maria, and me, to habitate on Mars. Since in the movie the main character gets stuck on Mars for 360 sols, Martian days, NASA decided to send us there in a similar situation and for the same amount of time. On Mars, waiting for us is a pressurized oxygenated station called the hub. Inside it, there is a field of grass with the same size of JVS field. Our mission was to design the hub so we could survive there long enough for the armed spacecraft to pick us up after 360 sols. The information we were given before we left was: the shape of the hub is a hemisphere. The floor of the hub is made entirely of grass and has the area of the JVS field. The armed spacecraft will arrive in 360 sols, and 1 sol is 1 day in Mars. The only food we have is 500 potatoes, and each potato can be halved and buried to grow 1 plant. At a minimum, we'll need to accommodate for the following in the hub: crops, beds, toilets, sinks, showers, and hairlocks. To solve our mystery, we had to think about how much oxygen a person needs per day, so that we know how much grass we'll need to survive for 360 sols, to keep it oxygenated enough. We also had to find how much oxygen does 1 blade of grass produces and how much oxygen there is on the JVS field. Besides, we had to find how to calculate the area of a circle, the volume of a hemisphere, and how many Earth days are 360 sols. More things we had to find were how many calories a potato has, how many calories a person needs per day, and which food is the best to provide it in order for us to grow. Methodology. So first, as the field has a complex shape, we had to divide it into individual shapes, such as triangles and rectangles. Once those individual shapes areas were found, they were then added together to find the entire area of the field. After, we calculate how much oxygen is produced by the grass on the available area of the field by discovering the number of blades of grass in 2 cm squared. By also finding how many 2 cm squared there are in the area meant for the grass, how much oxygen each group member requires to survive, and if the number of blades produce enough oxygen for all the group members to survive. Then, creating the design of the hub by using the measurements. After discovering what is the equivalent of 360 sols in Earth days by using the minutes in 1 sol and the minutes in 1 Earth day. After that, calculating the healthy nutritional intake for each individual group member by using their weight, date of birth, and height. After finding how many potatoes and soybeans can be grown in the hub by measuring the area where they can grow. After that, discovering the food intake per each sol so that there is enough food to last for 360 sols without starving to death. After calculating the shapes and size of the parts to build the 3D version of the model to put it all together. And finally, building the 3D version, conclusion, and evaluating it.
For the calculation, we started off by calculating the size of the field. As it has a unique shape, we decided to divide it into smaller individual shapes. So we made the biggest rectangle and then smaller and smaller rectangles, as well as 2 small triangles. We calculated each individual's length, width, and height, so that we could then calculate each area and add it up together to find the total area of the field. Numerical values for the volume and the radius. With those calculations, we then realized it was best to get a meter and whatever the decimal points were to use only for the soil on the ground for proper growth for the grass, the potatoes, and whichever other food we thought was best to grow. With the remaining space for the radius and the volume, we then realized that we should have a ground floor, a first floor, a second floor, and a third floor. We designed the hab into two main areas. One half just for the grass and enough sunlight to pass through to make the grass grow, and the other half, which would be our living space, and at the bottom with the food to grow. Before moving on to calculating how many potatoes we could grow in our limited space, we decided to discover what would be the ideal nutritional intake for each individual in the group per soul. To do this, we had to collect each member's weight, height, and date of birth. With the results we received, we then calculating what would be the ideal intake of only potatoes per soul. Once we had gotten our results, we realized through further calculations regarding the rows, spacing between the growing potatoes and the time it took to grow the potatoes, that the hab was unable to produce as many potatoes that we needed in the limited amount of time. Therefore, we calculated what nutritional values we were missing. These were a lot of protein and fats. This then led us to research and discover that soybeans and extra virgin olive oil would be the ideal foods to consume to give us a higher chance of survival on Mars. With further research, we discovered that the human body is capable of surviving 21 days living on just water. In other words, approximately 20 souls. And then we calculated the rows, amount of space we had to grow soybeans, and the rate at which they grew. Without our information about the food available to us, we then came up with what we would eat and during which periods we were while on Mars.
Some of the assumptions that we made during our project were that more oxygen is produced during the sol than carbon dioxide is produced at night. The hab is already built and prepared at our arrival. All group members are able to survive 20 sols without food and only water.
A potato! I haven't had a potato in 20 sols. I'm an Irish person finally eating a potato after 20 sols.
All soybeans have a diameter of half a centimeter. Maximum number of sols it takes to grow the potatoes and soybeans, all the food will be ready to harvest. These small amounts of food consumed can still be enough to perform many various activities successfully. We can bring soybeans and olive oil. The temperature is 70 degrees Fahrenheit, in other words, 21.1111 degrees Celsius. All potatoes are the same size.
Rose, it's dinner time.
Not another potato.
I hate potatoes.
We've been eating them for 360 days.
I cannot imagine why I wanted to eat this potato after 20 sols.
All soybeans weigh 5 grams each. Have communication with Earth, no one gets sick, and everyone eats the same amount of food, not taking into consideration their height.
Some of the limitations that we came across were the amount of food that we can bring to Mars, the amount of food we can grow on the hab, we didn't have any professional equipment, and none of us had actual experience on Mars.
Actually, we wanted to make our project as accurate as possible. To check how accurate some of our calculations were, we calculated the degree of accuracy and relative error. To do this, we used this formula. To first find the relative error of the field, we tried to find the lower and upper bound. We also wanted to take 3 measurements of the field's length and width. However, due to time constraint, we were not able to do so. Then we realized that finding the upper and lower bound of the field measurement was pointless, as we kept all decimal places the same in our calculations when finding the area of the hab. Then we went on to calculate the relative error for the number of sols we can go without eating anything and only drinking water. A human can survive on Earth for 21 days by only drinking water. On Mars, that converts to 20.47393365. However, for convenience and reality, we rounded it down to 20 days to ensure we never starve to death. We found that we had a relative error percentage of 2.314818%, and this is a very low figure, showing the accuracy for this was high. The website we used to find the conversion from Earth days to sols, which are Martian days, was accurate. We know this because it has in-depth research on space research from NASA and other trusted resources. This also cements our decision in saying the calculations are very accurate. Some questions which we asked ourselves were: rounding numbers, is that reliable? Do we really need accurate numbers? The answers to these questions are: rounding numbers can be reliable depending on the question. For example, rounding the days down is, and as do we need inaccurate answers? If we produce a hab and have grass laid out, will it produce enough oxygen? And will the gravity affect anything? Again, depending on the task, the answer to this varies. We need accurate numbers for finding the area of the hab and how much oxygen we need in it. However, it can only be as accurate as we make it with our limited resources. As for the last question, we predict it will produce enough oxygen based off our understanding, calculations and research. However, there is no way of knowing it.
Another part which could affect the degree of accuracy is the amount of oxygen each person needs and how much oxygen the whole area of the JBS field produces. The weight, height, and gender of a person really affects the amount of oxygen needed for them to function properly. We did not take this into consideration, and the variation of oxygen needed between people on Mars. This could affect the degree of accuracy, as we just assumed everyone would need the same amount of oxygen. The amount of oxygen needed by a person also varies when running, sleeping, also their height and their weight. We were not entirely sure how accurate the formulas we used are. We assumed they were accurate as we got the most subject-specific websites from businesses who deal specifically with math and science, but this does not entirely ensure that these formulas are correct.
As a group, we feel we have successfully found a solution to the best of our ability to be able to live on Mars. However, with the limited resources and time limit given to us, we were at a disadvantage before we even began. The thing we feel most confident about would be our calculations of the hemisphere area, also known as the hab. This is because we spent a lot of time and effort making sure these were as accurate as possible. We took many precautions to ensure our calculations had the best degree of accuracy so that it would be as relevant to real life as possible. Despite this, we found it difficult to do as we were given very limited resources to that of someone who would actually be given the task of sending people to Mars. Compared to someone with the experience, such as an engineer or scientist, who understand such calculations and situations due to their profession, we obviously lacked skills and prior knowledge, which put us at another disadvantage. Therefore, our calculations are not as accurate as we would have liked them to be, but as accurate as we could have possibly made them. We feel we have fared very well in the situation we were given and are happy with the overall outcome of our group investigation.
Another fault we made was that we were unable to calculate the percentage error initially. We attempted to calculate the percentage error using the upper and lower bounds, but we quickly learned this was an incorrect method. This is when we realized if we had taken the three measurements of the field, the width and the height, we could have calculated an average and then calculated the percentage error. Therefore, we were not able to find the degree of accuracy of the field. If we had more time, some questions we would look into would be: does gravity affect anything to do with our project? What would happen if we had a technical difficulty? Do we have communication with Earth? If so, is it constant? How big is the rocket ship? Will it be able to fit all the supplies we want to bring? Are there any health risks for going to Mars? If we get ill, what will the procedure be? And finally, is there life on Mars? We would look into these questions as they are all possibilities which could affect us while living on Mars. We presume that they will not initially affect us, however, they could play a major role in our survival. The longer we are living there,
We would only be able to look into these questions if we were given a deadline much further into the future and unlimited access to technology and in-depth research on Mars. Due to the deadline of the project, we were unable to take the measurements multiple times as we were under time pressure. Due to this, we could only measure the field calculations once. If we had more time, we could take these measurements 3 times at least, as this would enable us to calculate the percentage error for the accuracy of our calculations.
In conclusion, our trip to Mars would be a success. We would most probably survive. We were able to find out a few things that would have helped us stay alive, such as how much oxygen we needed during the day and night, how much food we needed in order to survive, how much grass we would need to grow the food, and how long it would take the food to grow. As well as we also found out how much grass we would have in the hab by calculating the area of the field at our school, since we would have the same amount of grass as the field in our hab. Our group was able to work together without any difficulties and came up with a design for our hab, which was a semicircle as shown here.